So to finish our discussion of 19th and early 20th century bridges, I want to look at one Swiss engineer and then a sort of family tree of American engineers who are faced with increasingly different problems than the bridge designers of the 19th century, but who also have different techniques, different technologies available to them. We looked at Robert Maillard and the beamless slab in the last lecture when we talked about concrete. And Maillard was certainly influential in the development of multi-story concrete construction and floor slabs, but he was best known for these bridges that he built throughout Switzerland. In particular, bridges for the growing automotive culture that was developing first in America, but then in Europe. And Maillard faced, of course, difficult problems. Switzerland has mountainous territory that requires all sorts of interventions to get roads that are useful for either carts to begin with, or eventually for automobiles and trains. Maillard worked in concrete in his bridge designs, just like he worked in concrete for his building designs. And you can see him developing some of the same principles that we saw, for instance, in Eiffel's work, where you want the bridge to be strong and stiff in some areas, but you want it to be ductile and movable in others, particularly where the bridge meets the foundations. You don't want bending loads in the bridge to be transferred into the foundations and try to twist them out, basically, of the ground. So Maillard worked in concrete, the material he was familiar with, and found ways to develop details that enabled his bridges to be slightly more agile than the concrete bridges, arch bridges, and things that had gone before. In his early work, you can see this beginning to develop. These are two road bridges in Switzerland, 20 years apart or so, but with some of the same principles at work. And on the left, you can see that the deck and the arch kind of merge into one another. The arch is definitely a beam arch, so it's undergoing a great deal of bending. But you can see that the arch tapers toward the ends, just like Eiffel's crescent bridges. And Maillard over-reinforces those, puts more steel in there than concrete, so that the joint works more like a steel connection and like a thin steel connection. So it allows it to move, to be a little bit ductile, somewhat like a pin connection. And then if you think about what the arch is doing, it's getting very, very deep toward about the 1/3 or 1/2 span of each half of arch. And then at the middle, there's another concrete pin connection. So Maillard here is finding ways to get the bridge to move just a little bit, even though it's in a very stiff, brittle material. The Tavanassa bridge works like a 3-hinged arch, but done in concrete instead of in steel. Waggital on the right has a hinge connection in the middle, and then stiff connections at the base that allow a more direct connection to the ground. But as you can see, it's rock, so it's a sturdier connection. And maybe most famously, Salginatobel, which he designs in 1930. This is his kind of masterpiece, and it's over, honestly, an impossible site. There is scaffolding that he has to build all the way up. He doesn't have the advantage that, say, Eads or Eiffel had in working with steel or iron, where you can sort of grow the building out of its supports. This does have to be scaffolded and formed. But you see in Salginatobel this very, very pure 3-hinged arch composition, where the arch gets thicker at the sort of quarter points or third points of the span, and those narrow down to a pin both in the middle and in the connections to the foundations on either side. Just a couple of details from Maillard's bridges, where you can see how the steel reinforcing becomes these sort of V-shaped elements on the left at the pin, and on the right, a pin in the other direction, a pin in the lateral direction, where the steel is giving the structure some ductility, some ability to move around a little bit as loads differ going across it. We'll come back to Maillard one more time when we talk about shells, because he was an expert at finding ways to apply concrete to an increasingly complex set of programs. But his bridges really are at the center of his career, and the understanding both that concrete was an appropriate material for bridges, particularly automotive bridges, but also that there were ways to get performance into them that mimicked that of steel construction. Crossing the Atlantic, we see a generation of bridges of increasingly long spans that are designed to provide automotive connections over straits or rivers or bays that were previously accessible only by ferry. And there is this kind of lineage, these three engineers who worked for one another over time, and who basically had this ongoing argument about whether bridges were pure engineering structures or whether there were aesthetics that could be attached to them, and also about what those aesthetics should be, right? Whether they should be what Montgomery Schuyler thought about the Brooklyn Bridge, where the structure speaks sort of plainly, or whether they should go back to the towers of the Brooklyn Bridge, and whether bridges demanded a sort of ornamental program in addition to speaking clearly about their structure. The first of these engineers is Gustav Lindenthal, who is German. He emigrated to the United States as a tradesman, as a stonemason, not as an engineer, and supervised construction during this Centennial Exposition in Philadelphia. Again, another knock-on from the Crystal Palace, one of these world expositions. He sort of rose up from supervising contractor to being a railway engineer, and went into practice at the very young age of 24, right? So very, very rapid rise. And judging by today's standards, not remotely close to what you'd expect in terms of engineering. But Lindenthal, a classic example of an empiricist, someone who comes up building their knowledge through actual on-site experience. Othmar Ammann was Swiss-born, also an emigre. He wrote a report on the collapse of a cantilever bridge over the river in Montreal in 1907, and this won him enough renown that Lindenthal hired him for one of the built bridges that we'll look at over Hellgate in New York City. He was frustrated by Lindenthal's approach, as we'll see, and he left in 1925 to basically work for his client, the Port of New York, where he designed one of the most important crossings, the Hudson River crossing, and where his philosophies, both about engineering and aesthetics, really came into conflict with Lindenthal's. Ammann had this incredible career not only as a bridge designer but also as a structural engineer. His name crops up in all kinds of important projects in the post-war era, but his New York career alone would make him one of the most important figures in the 20th century. He designed 7 major bridges and a number of minor ones for the Port Authority and what became the Triborough Bridge Authority, which, if you know the history of urban planning in New York, was Robert Moses' sort of fiefdom. So a great client if you're an engineer, because Moses built an awful lot. And Ammann founded one of the key engineering firms in America of the post-war era, Ammann and Whitney, in 1945. Another Lindenthal employee, though, David Steinman, who had worked for Lindenthal about the same time, formed a partnership that went in a very different direction. Steinman didn't do any bridges of his own, any major bridges of his own in New York, where he was based, but they did suspension and cantilever bridges elsewhere in the United States. He and Ammann, as you might expect from two very high-powered engineers coming from similar backgrounds, engaged in this kind of lifelong debate, really kind of fierce argument over what the aesthetics of a bridge should be. So to take a look at some of these, this is one of Lindenthal's earliest bridges, the Smithfield Street Bridge in Pittsburgh, which, as you can see, has some interesting parallels with the Saltash Bridge that we looked at in the first part of this lecture. The double arched, one on the top, a compression arch, the other on the bottom, a tension arch. And as you can see from the lack of buttressing on the left-hand side, these two cancel each other out. So there's no need for elaborate cabling or big anchorages. The tension in one, the compression in the other, actually make the ends work more or less in equilibrium. That shows that Lindenthal was certainly aware of what was going on in bridge design a generation prior. But if you look at the towers, you can also see that Lindenthal thought that the structure maybe wasn't enough on its own. The towers are providing just a little bit of stabilization for the pin connections, and they're of course supporting both the gravity load of the compression arch and the gravity load of the tension arch. They need a little bit of weight to make sure that, just like the finials on a Gothic buttress, the extra weight of the tower on top is going to help redirect the loads down into the foundations. But those finials certainly don't need to be as elaborately decorated as Lindenthal thought they should be. And Lindenthal essentially thinks of engineering as one thing and aesthetics as something else. And the aesthetics have to be basically applied, or they have to be added on to the bridge to make a legitimate civic statement. So this is coming in 1883. Whether Lindenthal had read Montgomery Schuyler's assessment of the Brooklyn Bridge, we don't exactly know. But it's a very, very different sensibility than Schuyler, who thought that in this case, the arches should speak for themselves, that there should be as plainly spoken a set of towers as is needed for directing the loads. But after that, the pitched roofs, the fake arches, the crenellations on top, all of those would have been unnecessary to Schuyler, and as we'll see, to others in this lineage. Automotive bridges take on a taxonomy in the 20th century that Myron Goldsmith, an engineer that we'll talk about in some detail in a couple of lectures, does a thesis project on, where he points out that there are certain spans that basically make certain bridge types much more efficient than others. And he says that, in the short sort of 400 to 500 feet zone, you have a number of options. You can do truss bridges, you can do plate girder bridges, all sorts of possibilities. But as those spans get longer and longer, you begin to find that there are sort of determined outcomes if you're thinking about what the most appropriate type would be. So continuous truss bridges up to 1,500 feet. Beyond that, you get steel arches. We'll look at a couple of those in a minute. Cantilever truss bridges like the Firth of Forth are better around up to about 2,000 feet. And then he says, once you're past 2,000 feet, you have no choice, right? The only thing you can do basically is a suspension bridge. The form of the bridge is basically determined for you. It's the engineer's job to figure out the best proportions of cables and things like that, but also to think about what the architectural or the aesthetic implications might be. Not shown here are cable-stayed bridges, which we'll look at when we look at engineering in the 1960s. But those fit somewhere between steel arch and suspension. So Lindenthal really is an early adopter of this idea that you design different types of bridges for different sets of spans. And interestingly, on the same river, just a couple miles apart, Lindenthal does two bridges, designs them at exactly the same time, and they could not be more different. The Queensboro Bridge, which passes over Roosevelt Island, he designs as a cantilever bridge. He takes advantage of the island to put his two main pylons, and then as you can see, the bridge grows out from those, much like the Eads Bridge or the Firth of Forth. On the right, you see the Manhattan Bridge, also built at the same time, but it has a much larger span, and therefore Lindenthal changes the construction type or the structural type to a suspension bridge. And you can see here, very similar to the Brooklyn Bridge, the cables have already been strung by a traveling jenny that just goes back and forth, stringing new spooling new strands of wire onto the cables. You can see that the cables are much higher than their final position because the weight of the deck at this point is only on the bits of the cable that are closest to the towers. And you can see that while there are some stylistic affinities, right, Lindenthal obviously very willing to let trusses speak for themselves in both the towers of the Manhattan and the whole structure of the Queensboro. They're very clearly two different types, and when complete, they give two very different impressions. The Manhattan has all of the kind of grace of the Brooklyn Bridge, maybe even a little more because the towers are steel now instead of masonry. The Queensboro Bridge, even Lindenthal thought was a bit much. He described it as unfortunately looking like a blacksmith's shop when he saw the finished product, but of course a legitimate, reasonable expression. You can see Lindenthal's tendency toward ornamenting his engineering too. The finials on top of the Queensboro Bridge are structurally unnecessary, as are the arches below it. And likewise, the Manhattan Bridge has these kind of crowning pieces on the top of the towers and arches where, again, they're really not necessary, right? These are comparable to the fake arch in the Eiffel Tower. For smaller spans, Lindenthal works with the steel arch. So this is the Hellgate Bridge that connects Staten Island to New Jersey. And you can see that he is fine going from a cantilever or suspension down to a more appropriate building type. Hellgate, you can see on the right, is built very much in the same way that the Eads is built, traveling cranes now walking out onto the bits of the arches that are completed. The arch is being supported by tension elements on the right and left. And you can see these massive stone piers that don't actually connect to the arch itself. The arch sits on two pin connections down at the base. What those stone piers are doing, though, is they are like the finials in a flying buttress. They're adding weight to the connections so that the loads flow more directly down instead of out. So they're helping to buttress the arch to take some of the thrust and to divert it more toward the vertical. Lindenthal, of course, thinks that these massive stone pylons have to be decorated, so there's a fairly robust program of neoclassical detailing on them. The arch, though, is pure engineering, right? He doesn't see the need to sort of annotate it or punctuate it with any additional ornament. So Ammann, his employee who goes on to work for the Port of New York Authority, gets involved in this dispute about where a bridge is going to go over the Hudson River, connecting Manhattan directly to New Jersey. Lindenthal and Ammann present two proposals to the Port Authority. Lindenthal thinks that the connection should go from Midtown to New Jersey. Ammann thinks that is overly ambitious. And he thinks instead that the bridge should go at 170th Street, where the river is a bit narrower. You'll notice in this sort of low-quality drawing, but still hopefully reasonably legible, that the center span in both cases is about the same. It's the backspan that Lindenthal needs to get over the additional space, the additional span, as the Hudson gets wider down around Midtown. Lindenthal's design requires not just a cable, but a trussed cable that you can see that is more complex. He has these bigger, chunkier towers. Ammann thinks you can do the shorter overall span farther north with less material and less span, and Ammann wins the competition. It proves to be much, much cheaper to build the bridge north to the north of Manhattan instead of at Midtown. And this is the genesis of what today is the George Washington Bridge. You can see the construction is very much like the Brooklyn Bridge, although like the Manhattan Bridge, the towers are now built out of steel instead of masonry. And you get a sense for the quantity, the scale of the anchorages that are required to hold the cables back, to keep the load of the deck from pulling the towers basically into the river. Bridge is completely successful. It is finished in 1931, as you see it here. Corbusier, the French architect, when he visits Manhattan a few years after this opens, he says the George Washington Bridge is the most beautiful bridge in the world. He said it's made of nothing but cables and steel beams, like he says, a reversed arch. Between water and sky, you see nothing but the bent cords supported by two steel towers. The structure is so pure, so resolute, so regular, that here, finally, steel architecture seems to laugh. And the bridge has become known for this exposed skeleton, right? The lightweight steel of its towers. What's not apparent to many people, certainly wasn't apparent to Corbusier, is that, in fact, there was a very robust ornamental program for this as well. Ammann absorbed some of his aesthetics from Lindenthal. Not only do you see the semicircular arches, which again don't really do anything, Those semicircular arches were actually designed to support a stone and masonry facade over the steel skeleton. So this on the right is what Ammann foresaw for the bridge. It would have been a very different experience than Corbusier describes, and one that I think would in fact have been aesthetically much less satisfying. Ammann went on to do these 7 major bridges over various bits of New York Harbor. The Bayonne, far to the south, is a steel arch bridge, and you can see that Ammann gets rid of the stone piers that direct the loads down into the ground. Instead, he brings the arch straight down into the foundations and puts the masses actually underwater. No ornament here, interestingly, and you can see that the steel arch feels much more graceful than at Hell Gate. Ammann also, his transformation later in his career was such that he designed suspension bridges, building on what he'd learned at the George Washington, and I think understanding that the pure steel without the masonry jacket was something worth expressing. So here, 2 of the suspension bridges that he built in New York, the Bronx-Whitestone in the upper right, and the Verrazano Narrows over the mouth of New York Harbor, the longest bridge of any type when it opened in 1964, where the steel towers are basically rendered in very, very minimalist solid planes. The round arches are still there, but they are rendered in a slightly more abstract way than the original George Washington Bridge would have. Now, set against that idea that the structure, again, can speak fairly plainly, that it can be a pretty pure visual experience, David Steinman, who is this other employee in Lindenthal's office, has a very different career. For one thing, he builds most of his bridges outside of New York, but for another, he strikes this kind of middle ground between Lilinthal's idea that you need to put traditional ornament onto the structure, and Ammann's growing idea that the structure can sort of speak for itself. Steinman's maybe best known bridge is St. John's, which is just outside of Portland in Oregon. And here he says he's inspired by the sort of verticality of the site to think about the steel towers of the bridge as sort of Gothic, right? That he wants to go back to every engineer's kind of favorite architectural period, the Gothic cathedrals, and he wants to borrow those forms. Now, the Gothic arch here has none of the structural advantages that it does when it's actually being built in masonry, right? The steel towers, as we've seen from Steinman's bridges, or from Ammann's bridges, can certainly handle the loads without the shape of the pointed arch. But Robinson and Steinman, Robinson is his engineering partner, they feel that there is a resonance not only with the Gothic cathedrals, but maybe also with Roebling's choice of Gothic arches for the Brooklyn Bridge, right? That this is a trope or a kind of made-up shape that nevertheless feels like an appropriate thing to sort of plaster onto a bridge. About the same time, he does this bridge over Narragansett Bay in Rhode Island, the Mount Hope. And here you can see that the Gothic arch is there, but it's a little bit more abstract. And it is related to the cross-bracing of the towers that are a more natural, I think, response to the function of a suspension bridge, right? The towers have to put up with a fair amount of wind load in addition to gravity. Whatever Steinman's aesthetic ideals, he saw himself in this debate or in this argument over empiricism versus theory, and he also thought that aesthetics had a role to play in how engineers came up with bridge solutions. So here he is writing in 1941, and he says that, look, theory and practice have both kind of come together, right? We have the analysis from theory that gives us much greater efficiency. And because we can be more efficient, our designs can be more graceful, right? More scientific, less material. Less material means less bulk, which means they necessarily appeal to that sense of the gossamer architecture that Schuyler was talking about. He says steel was originally used just along utilitarian lines. I think he's talking directly to Lindenthal here, with awkward proportions and angular forms. Think of the Queensboro Bridge. Then came attempts to secure architectural effects through the addition of decorative details. So there I think he's getting at Ammann's original idea for the George Washington Bridge, right? We have to clad it in masonry. And he thinks that what he is doing is finding the true artistic potential of steel by taking pure structural forms, developing them and perfecting them in proportions that will most beautifully express the dominant spirit of this material. So expressing the strength, the power, what he says is the grace of steel. Whether you do that by adopting kind of Gothic arches, as at St. John's, which the general public agrees is a spectacularly beautiful bridge, or whether it's something like the Mount Hope, where you're finding resonant forms that allude maybe more to the history of engineering, but come out of a pure interpretation of what the bridge is actually doing. I think Steinman, whether you agree with his particular choices or not, kind of gets it right, that engineering wants to design efficient bridges, but generally we want the aesthetics of those bridges to come out of that efficiency, not to be sort of slapped onto it. So to finish, I want to look at one last kind of great bridge project and a follow-on project that is maybe the most famous bridge failure, at least of the 20th century. The Golden Gate comes out of the same kind of appeal to building for the automobile over previously impossible stretches that the George Washington comes out of. It is really conceived, though, in the midst of the Great Depression, when labor and materials are very cheap and governments are trying to put as many people as they can to work. One of the great projects of the WPA era. The Golden Gate, like the Verrazano Narrows, a generation later, is going to go over the mouth of a harbor, in this case San Francisco Bay, and it is going to have to span something like 4,000 feet overall. A tremendous distance, something that there's no way you could get anywhere near with any of the earlier iron projects. The suspension bridge is really the only way to do it. Joseph Strauss is the engineer, figure that we've seen before. He has an assistant, Leon Moisseiff, and together they do the engineering and they also supervise the construction. On this section, you can see that there's a fair amount of earthworks. On the right, they have to cut away a small hill, or actually a fairly large hill, on the Marin County side. On the left, they have to actually bridge over an existing fort on the San Francisco side at the mouth of the harbor. You can see that the northernmost tower on the right is set pretty much on the edge of the land. The tower on the south, the San Francisco side, has to be caissoned into the earth below the bay. Strauss initially is a bit at a loss as to how best to do this. To handle what he knows is going to be a tremendous amount of deflection. He initially thinks about this kind of odd hybrid that would be both a cantilever and a suspension bridge. Cooler heads prevail, though, and he decides that the most efficient way to do it is going to be as a pure suspension bridge. It's a 4-year construction process, which is sort of incredibly rapid for a bridge this scale. But if you think about it, they're throwing an enormous amount of manpower at it. There's a huge surplus of labor, both skilled and unskilled, and that allows them to accelerate the process quite a bit. When you look at the towers, you can see that Strauss has taken the opposite approach as Steinman did at Mount Hope. So instead of cross-bracing, the towers of the Golden Gate resist crosswinds through these giant portal frames, moment connections between the verticals and these very, very deep horizontals. Strauss thinks that the towers that should basically speak for themselves. There's a very, very small amount of kind of stripy ornament that he applies, but he very carefully adjusts the proportions of the towers so that they taper slightly as they rise. They spread out, the columns anyway, spread out as they get toward the base, which helps with the wind bracing. And notice that there's cross bracing underneath the deck, right, where you don't see it. Strauss, I think, thinks that cross bracing is a little bit bulky, a little bit ungainly, and really he thinks shouldn't be part of the experience of driving across the deck. You get a sense for the scale, but also the kind of the treacherous nature of the construction. On the left here, the cables are being spun out. The deck, of course, not on there yet. On the right, an image that we've seen paralleled in a couple of other bridge construction sequences where the deck is sort of springing out from the towers, slowly putting its load on the cables. And if you look closely, you can see that the curvature of those cables does in fact change where the deck ends. The load on the cables is making a decided difference in their shape. The Golden Gate sort of famously has painted this what's called international orange. It contrasts beautifully with the green hills or brown hills, depending on the season around it. The orange actually is there mostly as a way to make the bridge stand out in fog, but the tower or the color works quite well. And on the left, you see the arch over the fort, and then the cables descending down into one of these massive concrete anchorages below. Strauss designed the deck as a truss to make it stiff. There was an urge, though, toward making these decks thinner and thinner and thinner. And you can see Leon Moisseiff there credited as one of the sort of second in command. Moisseiff would go on to design his own bridges, notably a similar suspension bridge, though a much smaller one, over the narrows that go into Tacoma Harbor up the Pacific coast in Washington. This bridge was notable for its almost literal gossamer proportions, right? Getting rid of the kind of bulky truss that had, in his view, marred the aesthetics of the Golden Gate, and designing instead the thinnest possible deck to accommodate the load of the cars going across it. Now, the Tacoma Narrows is famous because Moisseiff's thin deck did not quite account for not the lateral force of the wind, but the rhythmic force of the wind. The bridge, as you can see, is stiffened by girders on either side, and very quickly after the bridge opened, you can see that it had real problems. What's happening here is that the wind is blowing through the narrows at about 40 miles an hour. It's spilling over the girders, and it is creating eddies or turbulence. Those eddies end up getting shed, and as they get shed, the bridge picks up and then drops. And at exactly the right wind speed, the frequency of those of the bridge going up and down on either side matches its natural harmonic motion, and the deflection basically accelerates. You get this harmonic resonance that unfortunately made the problem worse and worse and worse. Interestingly, this is Moisseiff here on a particularly windy day, and as we'll see, a sort of a tragic one. Interestingly, you can see that around the center line, the bridge isn't moving so much, right? But it's certainly moving too much to be usable on either side. And finally, in 1940, when this film was taken, the harmonic motion became too much, and the bridge, as you'll see, suffered a fatal collapse. No one was killed, no one was injured, no one was on the bridge when this happened. But of course, it meant that the bridge, the engineering for the bridge, was in fact a colossal failure. Not because of any mistake that Moisseiff made, but rather because was this phenomenon that had never been made visible before. Right, the harmonic motion caused by wind is something that now generates an awful lot of the engineering of bridge design, but was really only discovered empirically, right? The theory didn't account for it. The theory had no way of predicting that. Instead, it was the actual experience of seeing what the wind would do to a bridge this thin and learning from that and using that then in the next generation of bridges, which typically had greater stiffeners, greater stiffening trusses, to prevent that sort of motion from happening. We'll come back to bridges occasionally throughout the rest of the course, but they, to me, present a kind of foil to some of the more traditional architectural advances that we've looked at. We'll look at what some of the other impacts that automotive technology and eventually aviation technology had on not only architecture but also on infrastructure as we go forward, in particular in the next lecture, where we'll look at architecture and power, both political and electrical and military.